We're talking about a technology that allows inexpensive, high-density packaging for semiconductors. Art, before we get into this, tell me more about the technology itself.
EoPlex was founded about 4 or 5 years ago by a serial inventor and entrepreneur in Silicon Valley, and it is based on an additive technology to produce high volume parts at low cost using various types of printing to deposit large sheets of different materials. It's not rapid prototyping, which people often think of when I say layers. It's ceramic and metal deposits that are put down using printing in large sheets to build up. We've made parts of 300, 400, 500 layers. Large sheet of them might have 10,000 at once. They all go into the furnace at once. They sinter together, negative material burns away, conductors form, dielectrics form, and the part is finished and comes out in a whole sheet.
And these parts can be conductive or non-conductive. You can make very intricate parts.
That's one of the big advantages. You're right. Since it is printing, the tooling is nothing more than masks, low-cost masks, and the complexity does not drive the cost when you make it this way. It's not like we're machining. So a very complex structure can be built pretty simply and at fairly low cost. And yes, you can use almost any ceramic that can be sintered, almost any metal, and various polymers as well.
Okay, so where does your secret sauce lie?
Well, we have 2 batches of secret sauce, so to speak. We have the secret sauce that most other companies have, which is technology, patents or trade secrets, how we produce things. And generally that's called secret sauce. We also have secret sauce, which is our materials that we're printing. In the printing industry, they'd call it printing inks. They sometimes call it printing paste. And as you can see, this is silver, and it looks a lot like sauce. So we have secret sauce that a French chef would be very comfortable with in consistency, maybe not taste, but we have about 200 of these.
Okay, so what's the problem then with the packaging that you're solving?
All right, we're looking at a conventional lead frame that's been partially molded as a demonstration. The backside, which you're looking at now, has the Kapton tape, which is helping to hold the product together. This is the conventional established technology. If we turn it over, we can see the molding compound, which will be applied when the chips have been mounted. But at the upper section, you'll see a very delicate structure. That's been done by etching away metal to create the center bond pad and then the connecting pins all around it. The chip will be mounted on that center bond pad that gives you the thermal and the mechanical structure, and then the wire bonding will happen from the points on each chip to those little pins that surround it. Then it will be molded, as you see in the lower half, and at that point it is finished. The Kapton tape can come off, and they have to dice it up because they're all connected. The metal is continuous, and you can't test them until you cut it apart. In addition, it's very crowded. The pins are very crowded because they all have to be connected. So everything that's there can't be independent. It has to be connected. That means it's a very congested structure. It limits the number of I/O, or the number of input and output we can get. Also, all that extra metal that's there, when it's diced up, some of it will remain in the package, and that will create electronic noise, interference. Parasitics is what it's called in the industry. And finally, since it was etched and plated, you've got the wet chemistry that is no longer desirable to have for that kind of processing. People would prefer not to have those nasty chemicals. Even though the industry handles them very well, they'd still rather eliminate them. So that's the conventional approach. Okay. What you would like to do is put down just the bare amount of metal for the bond pad, and independently have a dot for each pin that you want to have surrounding it, each row. What you're holding in your hand now is our product, which we call XLC, and it is a series of pads and pins that have been printed using our proprietary methods on a stainless steel substrate, which has a structure below that that's holding it on. That paste goes, the printing paste that created that, we can show you some of that in a moment, goes through a furnace at between 800 or 900 degrees, sinters the bond pad and the pins to high density. Then the customer can, that's our product. And now nothing is connected and nothing is shorted out. The customer can mount the chip on each of those bond pads, wire bond the way they normally do to each of the pins, and then overmold, and let's show you an example of that next. All of those bond pads, a chip has been mounted, wire bonded, and then this black molding compound, which is the standard in the industry, we're not forcing our customers to change or use anything different, has been molded over that structure, and then the customer simply peels off that molded structure when it's finished, and the proprietary layers that we've built into this product allow that sintered metal, which has gone through the furnace and held tight, allows it at that moment to peel off cleanly. This is the finished product. Each one of these is a die which will be diced, is a package which will be diced, labeled with the company's logo or identification number, usually in white. And before they dice it, you can now test the whole strip because there's no connection. Once the stainless steel comes off, it goes to recycling. There's no connection inside here except the connections you want. And you can test it in with a bed of nails, they call it, or a tester all at once. You dice it, you're only cutting plastic, there's no metal to cut. So your cutting is more efficient, the blade doesn't smear. You have, as you said, higher I/O, which means a lot more connections. It's a very thin package. You can make it less than 300 microns with I/O up to 500, we think, or more. And there's no nasty chemicals involved with the process. So it solves an environmental problem, it solves a manufacturing problem, and it's a lower cost solution.
How much lower cost?
Well, compared to the conventional method, it's about the same. Compared to the maybe 10 or 15% cheaper. Compared to trying to get the same effect by this double etch method, it's about 50% cheaper.
Okay, thank you.
Thank you.